Okay, so if I come over here and type FS to get the task record, you see this number matches the number up there. If I say X crosstalk 0x 7F D15028, I enter that's like the process ID. It's actually we just use the word task, not process. Anyway, if I do directory carriage return, then it sent that to this guy's input buffer. Now, if we can do this with Atom as well. Atom sits in a server loop. We don't need a carriage return with Atom. Anyway, so he sits waiting. Atom is like Atom's heap is like kernel memory. It never gets freed. So if you want something never to get freed, or you want code that's never going to get freed, then Atom include, and he'll include a file. So we go to demo graphics and fish, and we Atom include. Okay, so the wallpaper is Atom included. Now if we say task rep, this is a I don't use this very often. I just use a wallpaper normally. This shows a hierarchy of the tasks. Atom is the first task created, and he has children he has this is the terminal task. This is the frame grabber that's making this video. Then the window manager updates the screen 60 times a second and does a couple other things. Then there's a special server task on each core. It's kind of like the Atom for that core. Anyway, if you click on these, it'll kill the task. We don't want to do that. Atom never dies. His memory never gets freed. Anyway, so the window manager calls this routine 60 times a second to update the screen. It has a cache. Well, okay, first it has an array for the text. It writes the background, then it does the foreground. The foreground can be shifted according to superscript and subscript and marquee. You see up there's a marquee. That's done with shifting it off the axis, or off the grid. It calls that update window we talked about earlier. So the buffer is 8-bit together, but when it does the mouse cursor, and then it converts it to 4-bit. And it only does what's changed. It only writes what's changed to the VGA memory. That speeds it up a lot because the VGA memory is slow. But in the worst case, it doesn't speed it up. So we're going to talk about the scheduler. If we go to OS main, the scheduler goes in a loop. Round robin, and it doesn't save segments. It just saves registers and breakpoints. Breakpoints get removed when breakpoints are associated with the task. I almost never use breakpoints. They're with the window manager doing callbacks. The breakpoints are all screwed up. Anyway, so I do printf debugging. So it's round robin. And when it gets to a task, it checks if it's suspended or if it's waiting for a jiffy, wake jiffy. If it's not, it skips it, goes to the next one. It has some flags for hotkeys like Control-Alt-X kills the focus task, Control-Alt-Delete reboots, Control-Alt-Tab switches to the next. Now the multi-core task stays in a loop, and it gets a timer interrupt 60 times a second. It stays halted. You can wake it with a there's a software interrupt that'll wake up a core, non-maskable. Anyway, you either do a job or you do a spawn. A job is a one-time thing. A spawn is a task. So the Seth task either does the job that you tell it, or it spawns a task and then it continues. Multi-core is done explicitly. You tell what core you want doing a job. Anyway, the timer interrupt lets it figure out how much idle time it has. That's why it gets a timer interrupt. So we're going to talk about the file system. If it ends in .z, it's stored compressed. If we copy or move it to a name without z, then it's uncompressed. That's all there is to it. So this file is uncompressed. Now let's do a dump cluster, or let's do a directory star true this cluster, compressed, uncompressed. If you use the native file system, it keeps track of the uncompressed size. The FAT32 is all you need, because you can grow files. With the native file system, you can't grow a file. Anyway, so this tells the cluster. It's dump cluster. You give the cluster, and then a bool for if you want to write. So 0x, and then there's the cluster, and we do want to write. So here's the cluster. So in the file, we're going to change this text D, let's say FFFF, and it told us to press escape, so we press escape. Now we do a directory, and now this file starts with DFFFF. So we wrote to the cluster directly. Anyway, there's checksums when you use the native file system, and it's 64-bit, but it won't let you grow files. That's because there was a patent on the FAT. Now we're going to go look at, remember I talked about making a named name frame pointer. Basically, this is the entry in the symbol table, the task symbol table, that has a value. When we want to make a noise like an explosion or something, we make a record that has the high frequency, the start frequency, or the min frequency, max frequency, duration, and then we spawn a task that's in charge of that, and we have to pass it that record, and it sticks it in its symbol table, and then when this task dies, it knows it can free that. Anyway, so that keeps it from leaking memory. Anyway, so the compiler has a opcode table. Now, the opcodes are, there's no push AD. You can't push all registers. That only works in 32-bit mode. All stack operations are 64-bit in 64-bit mode. That means if you push a 32-bit register, it pushes all 64 bits. It doesn't clear them. Now, XOR clears the upper 32, or move clears the upper 32. Now push. My assembler doesn't recognize end of line, So you it tells by context when the instruction starts and stops. Sometimes you need a semicolon, like define byte or define U8. Anyway, you need a semicolon at the end of that. Anyway, my compiler has has an interrupt keyword. So if we dump this unassemble address keyboard interrupt handler, comma 100. Okay, so because we had an interrupt handler, because we had an interrupt keyword, it uses a IRET when it exits instead of a normal return. I think it pushes the registers it doesn't normally push, because interrupts, you want to save the registers. Anyway, so my compiler has an interrupt keyword that's like the old TempleOS had that. Anyway, so if you go to the lectures, PCI interrupt, these give some interrupt routines, and end of interrupt tells how to do that. There's a PCI rep tells the looks up the PCI devices. I only do HD audio, but that doesn't that support almost never works. So this tells the bus device and function. You might want to know about that. This is a nightmare. Anyway, another report is memory report. Memrep tells the status of the heaps and stuff. So the low memory has the OS main module and the VGA, and the Atom task has its own heap. There's a this tells just some. It's not 100% accounted for, but this tells the window manager has the buffers for the graphics and the device context and stuff. Anyway, and then the other tasks, there's an uncached heap. This is for if you need to make like for the audio buffers, you want the audio buffers allocated off of uncached for DMA. Anyway, so when you do malloc, you pass a heap control by default. It's either a task or a heap control. It tells by the signature. Anyway, there's now there's something called the BIOS 32. Remember we did that PCI rep? Well, the PCI registers are accessed with a special BIOS called, it's a 32-bit BIOS, so it has to change out of 64-bit down to 32-bit, and then it lets you read and write the PCI registers. Anyway, you might want to when you're debugging, you might want to intercept the fault handler, and you could make you recompile the kernel after you put some debug code in here. Anyway, it's kind of tricky, but if you I just thought I'd let you know. Anyway, so now there's map files. The way it knows symbols is when it boots, it loads map files, and map files are for the main OS main and for the compiler. That's how it starts. That's how it's able to do source debugging. It keeps track of line numbers and stuff. It's actually the map files have binary data in there.